G'day, welcome to our first video on differential equations, and these are fascinating things. They're very, very powerful equations used in science and maths engineering all the time. Very, very powerful modelling things and being able to sort of find different relationships between different variables. Very important field of maths. Also known as DEs for short, differential equations. Okay, so let's just have a look at that. What are differential equations? So differential equations are just equations that have derivatives in them. Okay, and so it could be any any forms of derivatives. So you get 1 plus that, it's like plus y or something like that. Doesn't matter what the configuration is, as if it contains a derivative of some sort in there, then it's a differential equation. So another one might be xy plus d squared y on dx squared equals 7 minus x or something like that. Again, it contains a derivative, so therefore it's a differential equation. Now, this one would be a first order DE, because the derivatives that it contains are only the first derivative. Okay, this one here contains a second derivative, so it's called a second order DE. And these ones are easier to solve than these ones, etc., etc. Just some other notation before we sort of get into things. The y dash, what that means is dy by whatever the variable is, but usually dy by dx, something like that. And y double dash refers to the second derivative. If we're talking about x, then it will be d squared y and dx squared. Okay, so that's just a bit of notation. And say y of 0 equals 3. What this means that y equals 3 when x equals 0, or whatever the variable is, and something else, y double dashed of -1 equals 4. What that means is that the second derivative is equal to 4 when x equals -1, etc. So that's just some notation that we need to know about differential equations before we get started. So what we're going to do is, the first thing that we're going to look at is just simply verifying. Oh, hang on. I want to talk about something before I get onto that. Okay. So let's just look at this differential equation here. dy by dx equals to 2x. Okay. Let's just have a look at what the solutions to these are. So to be able to do that, this is saying that the derivative of y with respect to x is equal to 2x. So the solution to any differential equation is to somehow get this dependent variable out as a y equals something. So we need to find out what y is equal to. Okay. Now, if dy dx is equal to 2, in other words, the derivative of y is equal to 2x, then y will be equal to the integral of 2x dx. Okay, so that's how you'd solve these particular equations. You're just finding the integral of that. So let's just do that. So therefore, y equals the integral of 2x is x squared plus a constant. And so that is the solution to this differential equation. So that's the differential equation, and that is the solution to the differential equation. Now, if we sketch what we just did here on a graph, how would we sketch that? Well, it depends on what the value of c is. We've got this integration constant here. So it could be anything. If c was equal to 0, the graph would look like this. Okay. If c was equal to -3, the graph would look like this. If c was equal to -10, the graph would look like this. If c was equal to 5, the graph would look like this, and etc. and etc. And basically, what you get from a differential equation is a family of curves. In other words, a family, they all have the same shape, but they just move up and down the axis, and it could be, there's infinite solutions here. Okay, so what we say that this is called the general solution. In other words, it's got infinite solutions. Okay, and so if you want to nail down which exact solution it is the answer, then what we need is a point. So if we can say, well, which point does this curve go through, we could say, well, actually, it goes through this point. The solution goes through that point. It's a known point to us. And so that we can say something like, say, if x equals -2 when y is equal to -1, just say, so that point there, then what we can do is substitute that into our solution, and we'll get a particular solution. In other words, we can find the value of c. Now let's just do that. So if we know this point, if we're given some point, we're given this, then what we can do is substitute that back in. So therefore, -1 equals -2 squared plus c. Therefore, c equals -1 minus 4, so that's -5. And so what we now have found the value of c. So therefore, y equals x squared minus 5. That's called the particular solution, because it's only one solution. One solution. And can you see the difference here? We've got a constant in here. That constant could be anything. And so I've got infinite solutions. It's the general solution. Here we've found out what that value of c is. We've got the exact solution. This is only this one solution. So this solution is just this curve here, the only one part of this family. That curve there. And so that's our particular solution. Particular solution there. Hopefully that makes sense. Okay, so now we're going to get into verifying, and I think I'll just do one example of this. Verifying solutions. And what verifying means to check. And so you might get a question that might be something like this. If we've got some dy dx is equal to 1 over y, over y, and we're told that the solution is y equals root 2x plus c. Okay, so we're told that that's the solution, and we're asked to verify that. Oh man, I keep on pressing this button, and I think it's really annoying. Verify that that is a solution to this DE. In other words, substitute this into this equation and check that it all makes sense. Okay, so I haven't written the whole question down, apologise for that, but you'll forgive me. Okay, so let's have a look at this. Our differential equation says the derivative of y with respect to x is equal to 1 over y. Okay, so firstly, let's find the derivative of y with respect to x. Okay, so y is equal to 2x plus c to the power half. Therefore, dy dx is equal to, half comes down the front, I'm taking the derivative here, middle stays the same, half gets subtract 1 off that, and then we need to multiply it by the derivative of the inside to multiply by 2. That 2 cancels with that half, and what we get is 1 over the square root of 2x plus c. And lo and behold, look what we have here. The derivative is equal to this, so therefore dy by dx is equal to 1 over, what is this down here? Well, that's y, so that's 1 over y. And so you can either draw a little square and colour it in, or QED, or as required, or something like that. You can write any of those things to show. I've shown you that this differential equation satisfies, this solution, this general solution, satisfies this differential equation. Now that's the general solution. So then the question might go on to say, find the particular solution. Find the particular solution if y1 equals 9. Okay, so you're given a point. Let's find the particular solution by substituting it in. So therefore we have, here's your general solution here. So y, 9 equals the square root of 2 times 1 plus c. Therefore, we have 9 equals the square root of 2 plus c. Let's square both sides. We have 81 equals 2 plus c. Therefore, c equals 79. So therefore, our particular solution, I just hate how it does that. Hit the button and it just like grabs the screen. Should try to not hit that button, shouldn't I? Y equals the square root of 2x plus c plus 79. That is your, that's the particular solution there. Okay, so if you're asked to verify a solution, all you need to do is substitute the things into that equation and make sure that it checks out, that the left-hand side is equal to the right-hand side. If that works, then excellent, as required, QED, whatever, and then you're generally asked to find a particular solution. So they can be a bit of fun. Most of them are much harder than that one, but just have a go at them and you'll see what they're about. Thank you.